Welcome to the video on the dependence of stability on conditions. So we want to now examine the way that phase equilibria change as the conditions are changed, as we change, say, pressure or temperature. So we want to know that we know that for a one-component system, the chemical potential is the same as the molar Gibbs energy of the phase, and that to have phases in equilibrium, to have two or more phases in equilibrium, the chemical potentials has to be equal. Right? That's what we saw in the last section. So at low temperatures, provided the pressure is not too low, the solid phase of a substance has the lowest chemical potential, and thus is the most stable phase. Note, however, that chemical potentials of different phases change with temperature in different ways. And so at some temperature, the chemical potential of another phase may become lower than the solid, like we saw that the chemical potential of a liquid phase will become lower. And at this point, a transition to the second phase is spontaneous and will occur unless it's kinetically limited. Provided it's not kinetically limited, then that phase change occurs. So let's look at the temperature dependence of the Gibbs energy. So the Gibbs energy can be expressed in terms of the entropy of the system, where we have this partial derivative. The partial derivative of Gibbs energy with respect to temperature at constant pressure is equal to the negative of the entropy. We've already shown this before. So because the molar Gibbs energy is equal to the chemical potential for pure substance, we can replace this del G with del mu, the change in the chemical potential with respect to temperature at constant pressure. Now necessitates, because remember that mu, our chemical potential, is the molar Gibbs energy, we now have to be talking about the molar entropy here. So because the molar entropy for all substances is positive, as the temperature is raised, the chemical potential of a pure substance has to decrease, and thus the slope of the plot of the chemical potential against temperature has to be negative. So if we look here, the slope of the solid line is negative. The slope of the liquid line of chemical potential with respect to temperature is negative. The slope of the gas line is negative. Now note that the solid has a lower chemical potential than the liquid or the gas, which is way up there somewhere. At low temperature, so the solid is the most stable phase here until we get to the melting point for that pressure, in which case now we're in this region where the liquid has the lowest chemical potential. And if we continue to increase the temperature, then the vapor phase, the gas phase, has the lowest chemical potential, and that is then the stable phase. So because the molar entropy for a gas is larger than for a liquid, the slope of the plot is steeper for the gas than it is for the liquid. The molar entropy for the liquid is higher than the molar entropy for the solid for most substances. Remember that this is not true for helium, but other than helium, it should be true. So most substances melt at a higher temperature as pressure increases. Although this is not true for something like water with a negative slope to the melting curve, but most substances expand upon melting and thus can respond to an increasing pressure by freezing in order to reduce the molar volume. But for something like water, that's not true. Reducing the molar volume necessitates moving from the solid phase to the liquid phase, because at the transition, the density of the liquid is higher than the density of the solid for water. So the variation in the chemical potential with pressure can be expressed like this. We have del mu, del P at constant temperature is equal to the molar volume. And this shows that the slope of the plot of chemical potential against pressure is equal to the molar volume of the substance. So increasing the pressure increases the chemical potential of any pure substance because the molar volume is positive. So for most substances, which is this plot here, increasing the pressure increases the melting temperature because the molar volume of the solid is less than the molar volume of the liquid. So if we have low pressure, if we increase the pressure from some low value to some higher value, note that we're also increasing where the liquid curve is. And so now the place at which those two curves meet, remember that's where the liquid phase and the solid phase are in equilibrium. That's where we'll have the transition from solid to liquid. That's where we'll have melting or freezing. That temperature increases. So for most substances, we have to increase the temperature if we increase the pressure in order to get the melting phase transition to occur. But for something like water or something else with that negative slope, increasing the pressure decreases the melting temperature because the molar volume for the solid is larger than the molar volume for the liquid. And so now, if we increase the pressure from here to there, we are moving the solid line, the solid curve from here up to there. We're also moving the liquid curve from here to there. But it's such that we're moving from this point, that chemical potential and temperature point, to this chemical potential, temperature point. Now note that this temperature is actually lower than that temperature was. So for higher pressures, we have to be at lower temperatures in order to melt water. So when a condensed phase is subjected to an increase in pressure, then the vapor pressure increases. So we can show that the vapor pressure P is related to the subjective pressure delta P. Note that this is a lowercase p, that's an uppercase P. So this is the subjective pressure applied, and the vapor pressure P star of the liquid in the absence of that additional pressure. So the pressure, the vapor pressure P is equal to P star, the vapor pressure of the liquid in the absence of this extra pressure, times E to the quantity, the molar volume of the liquid, times our change in pressure over R, the gas constant, times temperature. So that was the dependence of stability on conditions.